Hi, in this video, we will look at one example of the flexural bending stress. So here we go. You have a simply supported beam, and then we'll have a concentrated load right in the middle, and this load is, let's say, 100 Newton, and this entire length of the beam is L. Let's make a 5 meter long. Okay. So in that situation, without doing load shear bending diagram, because you already know what's this look like, right? For the maximum bending happens right in the middle, and that formula from the last one, you already know it's PL/4. So then you know it's going to be 100 Newton times 5 meter, and then divide by 4. Then that will give us 500 divided by 4. That's 125 Newton meter. Okay, so that's the maximum bending stress. Then for this problem, they want us to find what's the maximum bending stress. Then we're going to use our flexural formula, which is m/I, and SM have to be maximum point, and this Y have to be the maximum as well, kind of squeeze it up, and I is regarding the neutral axis. So in order to know the moment of inertia for neutral axis, you have to know what this cross section of this beam look like, and they give us it's a circular shape, and this it's a shaft. So this shaft, they give us the, let's see if it's 1 meter diameter. Okay, then we're going to go put in this formula. M maximum is 125 Newton meter, and if you cut it right in the middle, you got this cross section, and we know from last time this is going to be the neutral axis, and we do know it follow this. This is going to be compression, and the bottom one is being tension, compression, and you notice this profile is increased linearly, right? Because it's Y. When Y increase, this delta increase. It's a linear proportion. And so the Y max is happen to be at the top edge and the bottom edge. So that's going to be the Y maximum. Okay, so this Y maximum for this situation is going to be how much? It's going to be your radius, basically, right? So that's going to be half of your, it's going to be half of your diameter, D. Okay, and now let's thinking about this I, moment of inertia for circular shape. And I hope you already reviewed that. That's going to be 1/4 pi r to the power of 4, right? Okay. And since that's gonna be our moment of inertia, now let's look at this one. We're going to be able to solve this maximum. So go ahead. We know this is 125 Newton meter, and the D, this is basically your R. So your R, since this is diameter is 1, so that will be 0.5 meter. Let me put the unit along, so that's meter. And then it's 4 pi and 0.5 to the 4th. Then we actually can go ahead and solve this one. And make a note, I didn't do this way, but this is, you can actually solve this first. That's going to be reciprocal of the section modulus we talked about last time. Okay, so put all those in the formula. Let's do it. 125 times 4 divided by 3.14, then divided by 0.5 power of 3. So I have a value here is 1273.89. So that's going to be the sigma, maximum bending stress. And that value gonna give us in what unit? Let's think about it. All this is in Newton meter, and this is in meter to the fourth. So that's gonna give us Newton meter square. In other words, it's gonna be Pascal, right? And so I can change that to, it's gonna be 1.27, 1.274 kilopascal. That's going to be the maximum bending stress. So where does this maximum bending stress occurs? It's going to be occur in the midpoint right here. And however, when you look at that midpoint, where exactly occur? It's going to be occur right, I'm going to use a different, right this point and that point. Because, so this top point, you're going to get a maximum bending. And this is basically compression. And here you're going to get maximum of the bending. It's in tension. And may I ask you what's going to be the tension right here? What's going to be the stress right in the neutral axis? That's right, 0. Because right here, y is equal to 0. So that be equal to 0. So that's the example. Looking at the bending flexural stress, the cross section is circle. Now, this cross-section could be any shape, could be rectangle, could be I-beam. In that situation, you're going to find the moment of inertia for that particular cross-section, and the rest is very similar. Okay, now I'm done with this one, and I'll see you at the next one. All right, bye now.